Hi there, Mr. Sutton here, bringing you the IM3 Honors Chapter 6, Quiz 2 Review Solutions on Graphs and Equations of Rational Functions. Before I go ahead and find all the intercepts, holes, and asymptotes and try to graph this function, I'm going to go ahead and factor it because there's some things I need to know in order to get all that other stuff. So taking a look at my numerator, I need numbers that multiply to negative 30 and add up to 1. That would be, let me think, negative 5 and positive 6, so x minus 5, x plus 6. In the denominator, I'm looking for numbers that multiply to 10 and add up to negative 7. So negative 2 and negative 5 would help me down there. X minus 2, x minus 5. And I see very quickly that these x minus 5s can cancel if I want, leaving me with the simplified function of x plus 6 over x minus 2, which I'm going to need for quite a few things down here. So let's go ahead now and find the different intercepts, holes, and asymptotes, and then we'll graph this. For intercepts, I'll start with the x-intercepts. Those are going to be x values that zero out the simplified numerator up here of x plus 6. So if I set that equal to 0 and solve, I have negative 7 for my x-intercept, or negative 6 rather. And then for y-intercepts, I have to plug in 0 to the original function. So if I do that, everything conveniently zeroes out except for a negative 30 and a 10, which I can reduce to negative 3. All right, let's go ahead now and find some asymptotes. Vertical asymptote, that's going to be x values that zero out the simplified function. So that's going to be x minus 2 equals 0, so x equals 2 is our vertical asymptote. For holes, those will be x values that would zero out, make undefined the original equation, but not the simplified one. So we're looking for factors that got canceled out that would have given us 0 in the denominator if we had not canceled them out, like this x minus 5. If I set x minus 5 equal to 0 and solve, I have x equals 5 as the location of a hole. Now let's also think about horizontal asymptotes. Since my degrees x squared and x squared, second power, are the same for the numerator and denominator, that means I take the ratio of the lead coefficients, so the numbers next to the x squareds, which are both invisible ones, I take the ratio of those, so the division of those, and that's going to be my asymptote. So I have y equals 1 over 1, which is just 1. So we're going to go ahead and graph what we've got, and we'll see if we have enough information to keep going. We may need to get some additional points, but it's hard to tell until we actually put all this on there and see what falls where. So for x-intercepts, we had negative 6, and these grid lines are going by 2's, so here's negative 6. For the y-intercepts, we have negative 3, that's down here. For the vertical asymptote, we had x equals 2, so that's a vertical line going through 2. For the hole, we have 5, but we're not going to bother putting that on until we've actually drawn some of the graph that we can just figure out where 5 is on the graph. For the horizontal asymptote of y equals 1, that's a horizontal line going through 1 right here. And taking a look at this graph, I see that I've got plenty of information for graphing this to the left of this vertical asymptote. We've got these 2 points. Unfortunately, we don't know anything about what's going on to the right of the vertical asymptote. I don't know if I'm in the upper right or the lower right, so I'm going to need an additional point in order to figure out where I am and anchor this graph. For my additional point, I'm going to take an x value that's to the right of my vertical asymptote. Taking a look here, I'm thinking that 3 would help me out the most, and since 3 is not the location of a hole, I can use it in my simplified function here. So 3 plus 6 over 3 minus 2. Actually, let's go with 4. Just to be on the safe side, let's get a little bit further away and be on a grid line and go with 4. So 4 plus 6, 4 minus 2. So that's going to be 10 over 2, which is 5. So then I have the point 4, comma 5 right here. Okay, so let's go ahead and graph now. We have a branch that goes through these intercepts and approaches but does not touch the asymptotes on the left side here. We have another branch coming down across this asymptote, or at least near the asymptote, going through this point and going to the horizontal asymptote like so. And last but not least, we have this hole at x equals 5, which I'm going to put on the graph right there. There's x equals 5. So we're done with this one. For this function, I need to find intercepts, holes, and asymptotes and then graph it. Before I do that, it would be very helpful to factor this thing and see if there's any common factors that I can cancel out. So in my numerator, I notice I have a common factor of x that I can yank out of there, leaving me with x squared minus 4. And I can go a little bit further in the numerator. Since I have the difference of two squares, I can use my square root plus minus shortcut, split this up into x plus 2, x minus 2. Down below, I'm looking for numbers that multiply to negative 2 and add up to 1. That would be negative 1 and positive 2, so x minus 1, x plus 2. And I see that I can actually cancel out those x plus 2's. So there we go. That leaves me with x and x minus 2 in the numerator, x minus 1 in the denominator. Now that we've done that, let's go ahead and figure out our intercepts and asymptotes. For x-intercepts, those will be x values that zero out my simplified numerator. So x and x minus 2, setting that equal to 0 so that I can zero out the whole fraction. And I see that if x is 0 or 2, either of those numbers will zero out one factor and zero out the whole thing. So 0 and 2 then are the x-intercepts. All right, for y-intercepts, we're going to plug 0 into the original function up here. So if I do that, I zero out the entire numerator, so that's 0. I zero out most of the denominator. I have a negative 2. 0 over negative 2 is just 0. And I guess we should be expecting that because we had an x-intercept of 0. That's right here on the origin, and that's also a y-intercept of 0. But hey, now we really feel good about that. Moving on to vertical asymptotes. These will be things that zero out the simplified denominator, make the simplified function undefined. So if we set x minus 1 equal to 0, and solve, we got x equals 1 for an asymptote. Next, for holes, those will be x values that zero out functions that are factors that got canceled out, things that would have made the original undefined, but were removed so they don't make the simplified function undefined. So if we set x plus 2, the canceled out factor, equal to 0 and solve, we have a hole at x equals negative 2. For horizontal asymptotes, we have a top-heavy function, third degree versus second degree, numerator versus denominators, top-heavy. So there are no horizontal asymptotes. However, there is a slant asymptote that we can get if we divide the numerator by the denominator. And to make my life easier, because this would be a mess to divide with the original, I'm going to go with the simplified version here, and I'm going to distribute this out because that's the format I need it in. So I'll have x squared minus 2x divided by x minus 1. When I do that division, I'm going to get my slant asymptote. Since I'm dividing by a binomial, I'm going to need to use synthetic division. So let me set up my coefficients. So for my numerator here, I have a 1 for the x squared, a negative 2 for the x, and a 0 to hold the place of the constant that would be there, but there is no constant. For my box number, I'm going to use 1 because that's what zeroes out my factor of x minus 1. Bringing down that first one, we have 1 times 1 is 1, plus negative 2 is negative 1. And this is all we need, but we can keep going. 1 times negative 1 is negative 1, plus 0 is negative 1. We don't really care about the remainder. It's just the quotient that gives us our slant asymptote. So we end up with y equals 1x minus 1. And this is hopefully everything we need to graph this. We still might need additional points after we put everything on there, but let's go ahead and see. So let's start with the x-intercepts, 0 and 2. So here's 0. Here's the x-intercept 2. Next, the y-intercept, that doesn't give us anything new. We had a y-intercept of 0, already got that for the x-intercept. For vertical asymptotes, we had x equals 1, vertical line going through 1. And I see right away that I have points on either side of my vertical asymptote, which means I'm probably not going to need additional points. This is probably going to be everything I need, along with the slant I'm about to draw to graph this thing out. So my slant asymptote, we had x minus 1, so that's a line with a y-intercept of negative 1 and a slope of up 1 over 1, up 1 over 1, like so. And let me draw my branches now. So we have one branch on the left here, hugging the asymptotes and going through that x-intercept. We have another branch on the right, approaching the asymptotes and not touching them, though, and then going through that other x-intercept. And one thing we don't want to forget about is this hole at x equals negative 2. So now that I see what my graph is doing at negative 2, it's down here, I'm just going to put the hole right on the graph there. So it's usually easiest to wait until you've got the graph graphed out and then just kind of stick the hole on after you have that. For this problem, we're trying to solve for x, and we need to beware of extraneous roots. So to deal with this rational equation, I'm going to multiply everything by the LCD, the least common denominator. That gets rid of the fractions and gets x out of the denominator. So the LCD has everything I need to cancel out all of the denominators. So I need a 9 and an x in my LCD. And now I'm going to multiply everything by that. By everything, I just mean the numerators. So we have 7 times a 9x up there. And we have a 3 times a 9x. And the 4 also gets multiplied by 9x. Got to do the same thing to both sides of the equation. Going through now and canceling some things out. These 9's are going to cancel there. In the second fraction, the x's are canceling. And now I'm just going to go through and clean things up a little bit. So in the first fraction, we just have a 7x left over. Next, we have a 9 and a 3, so that's 27 if I multiply those. And on the right side of the equation, this comes out to 36x. Let me subtract that 7x just to get all the x's together. So that's 29x. And then if I divide by 29, I have 27/29 for my answer. Just doing a quick check, if I plug this back into the original, I'm not going to get anything undefined, no zeros in the denominator. So that means that this is a good answer. To solve this rational equation, I want to get rid of those denominators as soon as I can. My strategy for doing this is going to be to multiply everything, at least all the numerators, by the least common denominator, the LCD. That's going to have everything in it that I'll need to cancel out all of the denominators. Before I can find the LCD, though, I do need to factor this first denominator to see what I'm dealing with. So numbers that multiply to 12 and add up to negative 7, that would be negative 3 and negative 4. So we'll have x minus 3 and x minus 4 there, which is mighty convenient because that's what I have in my other denominators. So my LCD then, that's going to have everything I need to cancel out all of these denominators, is going to be none other than x minus 3 and x minus 4. Now I'm going to multiply that by all of the numerators here. So this 2 is getting an LCD to join it upstairs. This x also gets the LCD up there. And this 2 also gets an LCD. It's a lot of stuff to write out. The reason I do that, though, is so I can see what's left over after I cancel things out. So in my first fraction, the x minus 3 and x minus 4 both cancel. In the second fraction, the x minus 3's are going away. And in this last fraction, it's the x minus 4's departing. Cleaning up what I've got left over here, I've got a 2 left from that first fraction. That's very satisfying. In the next one, I have an x and an x minus 4, so I have to distribute that. So we're going to have an equals that we don't want to forget, and we'll have an x squared minus 4x. Next, we have a plus and then 2 being distributed times the x minus 3 here. So that's a plus 2x minus 6. And I see that I've got a quadratic with just an x squared. So I'm pretty sure I can factor this if I get everything on one side. So let's see here. We have an x squared, and I'll just move everything over to the right side here. Negative 4x plus 2x is negative 2x. And then if I subtract this 2 over to this negative 6, I've got a minus 8. All of that equaling 0. And as I suspected, this does look very factorable. I just need numbers that multiply to negative 8 and add up to negative 2. So positive 2 and negative 4 will do the job. We've got x plus 2 and x minus 4. Equaling both of those to 0 and zeroing them out, I have x equals negative 2 and positive 4. But wait, before I just call it a day, I have to make sure these don't make the original problem undefined. So if I plug negative 2 into all these denominators here, I'm not going to get 0 in any denominator, so I'm good with negative 2. However, if I plug 4 into the x minus 4 here, I'm going to get 0 in this denominator. Since 4 makes the original undefined, we actually have to cross that off. That's an extraneous root, and only negative 2 is our final answer.